You've probably heard that digital data is made up of zeros and ones, or binary characters. And it's pretty fascinating to think, well, with all of the fantastic digital applications we make use of today, how is it that our data is fundamentally stored in only zeros and ones? How is it we go from two simple numbers to the fantastically vivid and vibrant applications of being able to work with numbers and textual data and pictures and videos? How is it that we see our way out of just having two possible values to work with in memory? Well, that's what we're going to look at in this video. And we're going to take a look at both how do we think of things as symbolic representations, as well as what are some of the fundamental units in our memory systems. So let's get into it. I want you to imagine different meanings for the symbol you see on the screen. And I don't even want to put a name on this symbol yet, but these, the pink shape that you see here, what does that symbol mean? It depends, right? It depends on how we interpret this. This might be the letter V. So I might write letter as one possible meaning. Let's see what else. This could be the Roman numeral V, which would be a representation of the value 5, right? So we could represent the number 5 using the character V if we're thinking in terms of Roman numeral symbols. If we saw the symbol here with a word like below written above it, we know that this is an editing symbol that's saying, hey, at this point in the text below me, so there's a directionality, like we're using this symbol in a certain way that has meaning relative to something else. And so its context is giving it some meaning. You can imagine if we were looking at a map and you saw the same symbol pointed in this direction along a road, right? And you were looking at your GPS, that would probably symbolize your car or where you currently are in the world, a position or a direction or a marker of some sort. So in our daily lives, we can imagine many different meanings for this singular symbol V, right? Two lines that come together can have all sorts of different meanings. If you saw this in a sentence that was like, this slide is V interesting, you might assume that V was short for very in a modern texting dialect, right? So one symbol can mean many different things. It depends on how we interpret it as the reader and how we use it in context, right? So that's going to be an important fundamental lesson when it comes to understanding how binary is able to work and be applied in so many different applications. The same fundamental principle is at play. Data abstraction is this idea that how we are able to express complex ideas. And by expressing complex ideas, I mean in terms of sentences, in terms of forming images and videos. It's by taking some simple raw materials in deciding both how we want to combine those raw materials and how we want to interpret them, right? If all we had are lines that we could draw, we can form many different symbols out of two lines, right? So we can form two different symbols out of two different lines in their arrangement, right? A similar idea is going to be at play with binary. We're going to have two symbols available to us, 0 and 1. But we can combine many of these symbols together or form a string of binary digits. And in doing so, we'll have many different possible combinations, and we can assign whatever meaning we'd like as the designer of our systems to those combinations. Well, it turns out that over the past 50 years or so of computing, people have come to agree on some common standard interpretations of if we're trying to think about this group of binary digits as a number, here's how we're going to do that. Or if we're trying to think of it as a textual character, here's how we're going to do that. So systems have developed and become standardized, which is good because it means we can depend on certain properties when we're thinking about binary in certain ways. But the key idea here is that we can form and start to think in terms of more interesting applications and give more interesting meanings to simpler, less meaningful raw materials. And in our case, and in our world, we're thinking about digital bits or zeros and ones. The computers that we're working with are made of much simpler electronic devices, and there are just billions of them at play in your machine. In a future course, you might look at exactly how you combine these materials in order to build a computer. We're not going to get into that level of detail today, but fundamentally, when we think about binary, we're thinking about the presence or the absence of electricity in some component of our machine. And being able to control an on or an off, like a light switch, is what's happening on the order of billions of different electronic components in your single processor and in your memory cells. So your computer's memory is made up of billions of these bits or these memory cells in your dynamic RAM or memory. And I've numbered these starting from 0 and going all the way up to if you had 8 gigabytes of memory in your machine, which is not uncommon in a laptop today, you might have the highest memory address would be something on the order of 668 billion, not million, billion, right? There aren't many things in life that we have billions of, if you're not, Bill Gates or Mark Zuckerberg, besides the bytes in our computer's memory, right? Or the number of operations that our processors can carry out for us. So these are a gateway to having a lot of something. And what we do with that something is what we wind up finding as the important application of computer science and computation. So there's very understated ellipses here that represent the numbers between 63 through 68 billion. Right? Each of these cells can store 1 bit of data. And our programs are going to be responsible for modifying or storing different values in our computer's memory. How we group these together to form what we think of as memory objects, and that's different from how you think of object-oriented programming or objects in a language like Java, has a slightly different meaning. A more primitive and lower level meaning of the word object is it's a grouping of bits in memory that we assign some coherent meaning to, and we treat as a unit or a fundamental concept. So we could have a number that might be 64 bits, and we would treat that number as a 64-bit object in our computer's memory. This duplication of terms can be a little confusing at first when you're coming from a world where you think of objects in the object-oriented sense. In the systems world, objects tend to refer to meaningful clusters or groupings of data in memory that we can interact with and think of as a unit or start to put some meaning to, or a level of abstraction to. We decide how to group these things together and form our objects and how big our objects are going to be in memory. And that's going to have a direct impact on how many different values can be represented in one object, right? Each time you add another binary bit to an object, you're doubling the number of possible permutations or possible symbols that that object can represent. There are some common groupings of bits that have some names that are important to know as we're working in a systems programming language. The first is a word. A word tends to be system specific or architecture specific. What I mean by that is your computer is most likely a 64-bit processor. And by virtue of that, it's probably made the decision that it's going to think of a word as being 64 bits. In a future course, you'll learn that how we access memory tends to be organized, and address memory, in fact, tends to be organized relative to word sizes. In our operations, think in terms of words so that we can move 64 bits of memory or 64 bits of data from memory to our computer or back very efficiently, and that's considered de facto. If we had a 32-bit processor, the system architecture might choose a 32-bit word size. But when we think of a word size, and you hear that, we're talking about what is sort of the most efficient and commonly used size of memory or data that we're going to be moving around in our system at a very low level. When we're thinking of the word byte, a byte is always 8 bits, right? So a byte is made up of 8 bits in memory. And we'll look at how these bits are arranged when we start looking at exact representations in a future lesson. When we think about a byte, if you take only half of a byte and make it 4 bits, we call that a nibble canonically. And for a lot of what we're about to focus on in terms of specific representations and concepts, we'll look at nibbles because it's a little bit more manageable. And by only having 4 bits, we would have 2 to the 4th different possible values we can represent here, or 16 different combinations we can form of zeros and ones within a nibble. But 2 nibbles together and you've got a byte, right? When you're working in memory, as I mentioned, words tend to be how some architectural decisions are made in your processor, but typically you're able to address memory at the byte level regardless, because many of our data types, specifically textual data, is often each character in a string in a traditional older ASCII string is only 8 bits. In a more modern Unicode text string, characters might be 8 bits or a byte, but they might be multi-byte as well, depending on what type of character or what character we're trying to encode. So we'll see many different examples of where these words and the idea of grouping different sizes of blocks of memory together gives us different properties in the types of objects we're working with. And so if we're working with an integer value, if we choose an 8-bit or a byte-sized integer value to work with, we can hold fundamentally far fewer different integer values than we can if we were to think about a 32-bit integer or a 64-bit integer. You can imagine 2 to the 32 is much bigger than 2 to the 8th, right? Typically, you'll see that these groupings of bits are orders of magnitude that grow by doubling, right? We tend to, because of the binary system, you're always going to be grouping in terms of 2, 4, 8, or powers of 2, effectively, is how you would think of it. Why the 8-bit byte? Well, this is a fun story for anyone who's studying computer science at UNC or just wants to know a little bit about computing history. There was a time where Fred Brooks was working on the System 360, which was a fundamentally important computing system developed at IBM, and he was the program manager for it. And there was a big debate between 2 teams on whether to go with a 6-bit byte or an 8-bit byte. And I want to impress upon you that this decision was a human decision, and it was one that Fred played a fundamentally important role in deciding. And he ultimately decided, after much debate, that the team would move forward with the more expensive and more complex 8-bit byte. And the reason for this was so that the textual characters that the system could encode would not only include uppercase letters, but would also be able to represent lowercase letters in 1 byte of memory. If you only had 6 bits, you wouldn't have enough different possible symbols you could form from those combinations in order to have both, as well as all of the other symbols that you'll want to have in a character set in order to have a meaningful digital system. So we can thank Fred for the 8-bit byte and a fun bit of computing history there. So that's a brief introduction into memory and how we think about grouping different sizes of memory. And once we have groupings, we can start to think of how we interpret those groupings as objects based on whether we want to be working with numerical data, textual data, or other kinds.